Okay, so let me talk about two exercises showing isomorphism. And I want to show that the flow of these two exercises is very similar. The structural outline and the steps that you need to take are similar. So let's kind of give you a recipe for proving these isomorphism proofs. All right, so the first one says, prove that C star is isomorphic to the subgroup of GL2 of R consisting of matrices of the form AB minus BA. And here it's understood that where A and B are real numbers. Okay, because this is GL2 of R. Okay. Now let's start with this. So first of all, let's identify the two groups. The domain is C star, and the isomorphic group that's the range is this subgroup. So let's give that a name. We'll say let H be the subgroup of GL2 of R consisting of matrices of this form A, B minus BA. Okay. And here we should say this is a subgroup of these. I didn't ask you to verify that this is a subgroup. Let's just assume that it is. Okay, so let's show that C star is isomorphic, so we'll have to define an isomorphism. So we'll have to define a function, and we'll call it phi because we've been defining isomorphisms as phi, and this goes from C star to AB minus BA. By, and then you're going to define phi of A plus BI, and I'm not going to put too fine a point on it, but you have to fill this in this blank. What are you going to define phi of A plus BI to be? So what you want to show is that phi is 1-to-1 onto and preserves operation. Okay, so that's what you have to do. This is standard stuff from the functions chapter. 1-to-1 means that if you have phi of A plus BI equals phi of C plus DI, that means A plus BI equals C plus DI. And it preserves the operation. Well, onto means that every element of this subgroup, so here I shouldn't say this, I should call that H, that would be better. Let me just call it H. Okay. All right, so the onto shows to take an arbitrary element of H, then you can find A plus BI such that phi of A plus BI equals that element, and preserves the operation. Just verify this statement. You remember the statement that you're going to want to have phi of A plus BI times C plus DI is equal to phi of A plus BI times phi of C plus DI, where this multiplication is matrix multiplication, and this multiplication is complex multiplication. All right, you take the complex multiplication, then take phi, and you get the same result if you take phi of the individual complex numbers and take matrix multiplication. Right now, so that's the order that you follow. That's kind of a template or recipe that you follow to show isomorphism. For 11.3.16, it's going to be very similar. Okay, for 11.3.16. Let's see, you have your group G, so we'll let G equal S3 over A3. Now it'd be helpful if you listed the elements, I think. Okay. And in this case, what you want to do is define a map define, we'll call it C from G to Z2 by, and here I would suggest that you define C element by element. Element by element. Okay, you've got a limited number of elements of G. You can just define the C of each element of G as a value in Z2. And then you can just verify that C is 1-to-1 onto and preserves operation. Now, how do you show that it preserves the operation? Well, you can do exhaustive. You can just exhibit all possible operations. Okay. Or you can show the identification of the Cayley table. Show that Cayley table of Z2 can be obtained from Cayley table of S of G by replacing elements in the margin. Or I should just say by replacing elements. Now, what do I mean by that? Well, there's an example here where we showed the isomorphism between Z4 and the fourth roots of unity. I took this Cayley table for Z4 and I made this replacement. Every time I saw a 0, I replaced a 1. Every time I saw a 1, I replaced an I, and so on. I got this table. It turned out it was exactly the same as the table for the fourth roots of unity. That shows that we have isomorphism there. All right, so that's all you need to do. So it's kind of a recipe how you show isomorphism between groups. There's some details that differ, but the general outline is always the same.